So as the last one, what I wanted to talk about a bit is I wanted to introduce you a bit to looking also at your projects. I saw some of you have an interest in machine learning. And so I thought that maybe it might be interesting to look at one specific application of machine learning to lattice gauge theories, which I've also personally looked at a bit. Before we go though to that, I just want to give you some references. So during the past few years, there has been some activity in introducing, machine learning concepts in the analysis or the simulation of lattice gauge theories. Okay, I mean, I've grouped them here into these three categories, but of course, I mean, this is not. This is just my grouping, roughly speaking, you can think of some methods that use machine learning in order to detect sort of bulk phenomena or classify parameters in the system, such as identifying phase transitions and critical points. There are some references here. Then I have some references on the analysis of machine learning using the analysis of correlation functions, and that includes in reconstructing PDFs, pattern distribution functions, and there are some recent works here. And of course, these lists are non-exhaustive. Apologies if your favorite reference is not in here, but these are just some examples, and then there are other references in there. This machine learning for the analysis of correlation functions, specifically in reconstructing PDFs, is something that's sort of similar to what is done experimentally. And now people are also doing it on the lattice. And then the last one here is machine learning for accelerating or just for improving the generation of field configurations. Okay. And this actually, the last one is the one that I want to sort of talk a bit about today, on what the main concept is and how this works, get a bit into the technical details of this. By the way, if you want to ask any questions as we go along, then please feel free to do so. Okay, so as I said, in this lecture, I will talk about a bit of some methods for using machine learning for the generation of field configurations. Okay, and to do that, I want to just introduce some concepts. This we've also done in some previous lectures, but just to get the notation down, let's say. So, in lattice gauge theories, we typically require computing integrals such as the following. So here we've already Wick rotated this so that you have a real probability here. So what you want is to integrate over the field configurations, right? So over the field variables with some weight here, e to the minus the action, and some observable, and this defines the expectation value of the observable. And you also have the 1 over z, the partition function there, right? So phi are the fields with d degrees of freedom. Then O of phi is some physical observable, which we want to compute the expectation value of. And then S is the action, and Z is just you can see it as a normalization probability. So that's equivalent to saying that you want to measure these observables of phi with a given probability of phi and taking the integral. So it's equivalent to, to interpreting this factor here, e to the minus s pi over z, as a probability. Okay, and when we do this, then we can basically talk about Markov chain Monte Carlo. So in carrying out that integral that I showed in the previous slide, to carry it out, one can define a so-called Markov chain process in which you generate a chain of the fields that you're interested to generate, starting from an arbitrary field. And then if you define this transition probability from going from one step to the other, then you can show that these fields that you generate here will indeed converge to the desired probability if this T, this transition probability, satisfies these conditions. So the first is a ergodicity, which basically just says that in a finite number of steps, you can go from any field to any other field for a finite number of steps. So if you apply this transition n times, finite n times, then you can get from any field to any field. But also that this balance is satisfied, which basically means that this probability, this transition is symmetric under the probability. Okay, now, right. So if you can find a transition which satisfies these two conditions, then you can have a Markov chain, and the phi's will satisfy P of f, which is e to the minus action of f of z. And the standard way of doing this is using metropolis sampling, which is now I have these P tilde phi prime. So I'm producing these field configurations, not with the desired probability P of phi, which is e to the minus action of phi over z, as I showed in the last slide, but I have some distribution that I know how to sample from, which I call P tilde of phi. So I draw these proposals using P tilde of phi, and then I accept them as the next configuration in the Markov chain with this probability, which involves both my desired probability, and P tilde of phi, which is the one that I'm actually drawing from. So I accept phi prime with this probability, otherwise I accept the next step as the same step, right? So one can show that this, and it's not the purpose is here to show this, but this one can see that this can show that this satisfies a ergodicity imbalance. And it allows, importantly, it allows us drawing from an arbitrary distribution, P tilde phi prime, right, which we know how to draw from. For example, we can draw these normally or uniformly. So a probability distribution that we know how to draw random samples from. And another cool feature, of course, is that in computing this probability to accept the trial configuration phi prime, you only have ratios of the original probability, which means that this partition function, which in general is unknown, right, because it's the integral of overall samples, cancels out. So because it cancels out, you don't need to know z explicitly, and you only need to compute differences such as these, which are easier to compute. The action is generally easy to compute. So if you have a Markov chain, which you've created using this metropolis step, then that means that your configuration, so your phi fields are distributed according to your desired probability P now, right? You drew them with P tilde, you did the metropolis step, so now they are distributed with P, which is the action. And that means that expectation values can be just averages over the fields, right? And statistical errors scale, because this is Monte Carlo, like 1 over square root the number of samples that you take. Okay, and before we go on to talk about how machine learning enters here, we should introduce some concepts in carrying out these Markov chain processes. So the first one is so-called acceptance rate. So I'm going to go a step back. So you can see from this metropolis step here that if P tilde, as a P tilde of phi prime approaches P, then basically this ratio becomes 1, and then all your configurations that you propose will be accepted. And that's, I mean, that's sort of intuitively correct, right? So if you know how to draw from the real distribution, then the metropolis step will basically accept every probability. If P tilde is somehow a very bad, if P tilde is a very bad choice, let's say, is an unfortunate choice of sampling, then you will get more and more rejection. So this ratio here will be far from 1, and so you will be more likely to not accept a change, which means that you'll get a Markov chain with many repeated configurations. Okay, and so we have this concept of the acceptance rate, which is basically once you've, for a given number of trials, what is the ratio of those that were accepted versus those that were not accepted? And sometimes, or usually, this can be tunable, right, in the way that you define P tilde. Okay. Another concept is sort of, yes, sure.
But that P tilde is not the transition probability, or does it not have to be?
No, it doesn't. No, it doesn't have to be.
Okay. Yeah. Sorry. Thank you then.
Yeah. Then autocorrelation, which I will use rho of tau, is, well, it can be defined in various ways, but you can think of it as the probability of having tau rejections, consecutive rejections, with the definition that we start from 1, so rho of 0, 1. You can also define this differently for any given observable, but in general, you can just also define it equivalently for having some number of rho of tau being the probability of having tau consecutive rejections. And then autocorrelation is loosely the value of tau for which this autocorrelation time, autocorrelation goes to 0. So the distance at which this autocorrelation goes to 0. In other words, what is the maximum number of rejections in a row that I have in a given Markov chain? It can be loosely defined as the autocorrelation time. And more formally, you can define it as this integral, right? So if you sum all of if you integrate over rho of tau, then at some point it'll become 0, and then you stop adding to the sum. So this is sort of a bit more formally what is written here in the previous bullet point. So that's sort of correlation time, and I'll show you some examples of that. And then I will define here critical slowing down, which you can think of as this tau int diverging, so becoming exponentially large as you approach some critical point in the theory. Okay, and just to show you an example of what this looks like, I mean a very standard case where you can see this is in the U1 pure gauge theory. Yes, so where you have U1 fields, right? Two-dimensional U1 fields is similar to the exercise we did yesterday, but you just have gauge fields now. It's pure gauge, and then you have the plaquette basically action, and then the topological charge that can be defined in this way as the argument of the plaquette. So basically the angle in the plaquette, right? And what I'm showing here is on the x-axis is the number of hybrid Monte Carlo iterations that you do, right, in this Markov chain. So hybrid Monte Carlo, which we covered in the second lecture, is basically just a way to propose new configurations, right? So you add these momentum fields, and then you integrate using molecular dynamics, and that's a way. Basically, it's a specific choice of p tilde, right? The hybrid Monte Carlo. It's an algorithm that implements some choice of p tilde. And okay, and so here we have the beta, which multiplies the action in the exponent, right, or the inverse temperature, and we're moving towards larger betas from bottom to top, and then we're plotting the topological charge that you get as a function of the number of hybrid Monte Carlo iterations. So the Markov chain basically is running from left to right in all these plots. And what you can see as you go to larger beta is basically these, you know, that the topological charge, what we say, it freezes. So basically it stops changing, which basically means that you have all the more rejected changes here. So if you were to compute the autocorrelation, as a function of the separation for these quantities, then you would get something like this, where you see that rho of tau, right? So here I'm plotting rho of tau, which I defined before, for the case of the topological charge. So more formally, you can define it like this, where the observable now is exactly the topological charge. And you can see that for small beta values, then rho of tau immediately goes to 0, right? In just a few iterations. Whereas as you move upwards, and this is very slow, that you see rho of tau going to 0. And then, yes, you can also see where this is going. You can compute the integrated autocorrelation time. I'll just step back. So the integrated autocorrelation time, which is just summing rho of tau, starting from the first point. And then if you do that, then you can see on a log scale here, this is tau int, you can see that basically is what I told you before. So you see critical slowing down, which basically means that tau int, the integrated autocorrelation time, increases exponentially with a parameter of the theory as you reach, you know, a critical point of the theory. Okay. All right. So this is all background to explain a bit what we're looking for in these methods, right? So I'll come to it now. So this is just the half of the slide that I had before. Again, we have a given choice of p tilde, which previously was this hybrid Monte Carlo. And then this p tilde is unfavorable the choice that we made is unfavorable for the case where you reach this critical point, since basically we get continuous rejections. These so-called flow-based generative models, which are the machine learning models that we will talk about today for Markov chain Monte Carlo, the idea is to use neural networks instead of, you know, as p tilde. Sorry, well, as a p tilde, we use a neural network. So we use a neural network to propose these phi tildes, and then we'll talk a bit, and then we train. The idea is to train this neural network so that p tilde is as close to, you know, p as possible. Okay, so that's the main idea. Right, and before I go into the details, I just want to remind a bit about how we transform distributions in general, right? So no machine learning now, this is statistics. Huh? So if you have X a random variable with a probability density function f of x, then if we transform this variable with some function h, then the resulting variables y are distributed according to P of y, where P of y is given by this expression, right? So this is basically f of x, so the original distribution times some Jacobian function. So for one variable, so one very trivial example, right? Very trivial example, you have f of x, which is just a uniform distribution, right? And then you feed all these uniform random numbers into a logarithmic function, minus log n. So what will you get? Well, okay, so you have the uniform distribution here. So you have the x's distributed like this. So I'm plotting on the x-axis x, and the y-axis is the frequency, the normalized frequency of how how frequent each x occurs, right? So this is a distribution, and of course these are equally, all x's are equally probable, which means f of x is 1. So you have a uniform distribution. Then these x's I feed into a logarithmic function, but what I get as a distribution, of course, is e to the minus y, right? So the y's are distributed as e to the minus y, because to invert h, it's related to the inverse of h and the derivative of the inverse of this function with respect to the transformed variable. Okay, so that's how we transform probability distributions. And this generalizes to, you know, vectors of random variables. So if now the x's are a vector, right? So if we have y equals h of x, right? So x now is a vector of random variables, and so this h function is a vector function, right? It returns a vector, and so y is also a vector. Then notice that the Jacobian is now a matrix, right? So it's so you have hi and hj there, and so it generalizes to being a determinant of the Jacobian, and again you have this term which is the original distribution. And just as a simple exercise, if you really want to see how this works, I mean, if you ever use this well-known Box-Muller transformation, which basically takes two uniformly distributed random variables u and maps them into two normally distributed random variables z. So basically you have, so the original distribution is again uniform, but the h function that you're applying now has two components, right? So it takes the logarithm, it relates to the logarithm of the first variable, and then the cosine of the second, and the logarithm again of the first variable, but then the sine of the second variable. So if you compute this here, this transformation here, given this h that I defined here, then you will see that the resulting variables are indeed distributed normally, right? So they're independently normal. So z0 square and e to the minus z1 square. Right, so that was my refresher on how one transforms distributions. And this is exactly what these flow-based generative models use, right? So the idea is, given a set of random variables z that we can draw from a distribution that we know, right? That we know how to draw from, for example, R of z, then we need to find a transformation such that this the transform distribution p tilde of f of phi closely approximates our desired distribution, right? E to the minus sy over z. So, oh, by the way, because I'm following the notation of one of the papers that I showed before. So this basically what we called H before is now called F inverse, and what we called H inverse before and appeared in the determinant is now F not inverse, so F forward. That's just, yeah, I'm not trying to confuse you. It's just I'm following some literature. Okay, so the requirements is, of course, that this f of phi must be invertible, right? Because both its inverse appear and its forward version appear. And of course, this derivative must exist, right? And must be easy to compute. And one solution to that is to use these so-called real non-volume preserving flows. So the transformation that one does, I didn't mean to, yeah, okay. So the transformation basically that one does is you split your variables into two in some way, right? Either you take the even sides to be phi A and the odd sides to be phi B, or the upper half of the vector to be phi A and the bottom half to be phi B. It doesn't really matter in the general case. And you apply this transformation, G of phi, where you leave one half untouched, and then the other half is basically a linear transformation where the parameters of the linear transformation, right? So the other half is being scaled and shifted. That's why this is S for scale and T for translate. So it's being scaled and shifted. And the scale parameter and the shift parameter depend on the half of the vector that you left unchanged. Okay. So this G of phi indeed maps from the same number of elements to the same number of elements. And then in this case, okay, we'll talk about it a bit later, but these S and the T can be neural networks that have as input a half vector and output a half vector, okay? This symbol here just means element by element product, right? So the first element of phi B will multiply the first element of e to the S phi A, the second of phi B, the second element, etc. So it's just an element by element product. Okay, what's special about this choice? Well, okay, I just wrote it here again so that we can see it. So first of all, you can invert it, right? So you can write G inverse of Z and is just given by this expression, where you see now that T inverse and S inverse you don't need T inverse and S inverse. So you can write the inverse just as a function of the same functions T and S that you used in the forward case. So this is relatively easy, let's say, to invert once you have a T and an S defined. And the other interesting aspect is that the determinant is also relatively easy to compute. So let's take this step by step. So again, we said the determinant now is a matrix, right? So basically you need to take the determinant of each element of G with every other element of phi, right? But broadly, you have this, you can block it up into this 4x4 matrix where you have, for example, the even derivative here, the odd even derivative there, the even odd derivative here, and the derivative of the odd elements over the odd elements there. And you can see that, okay, if we're doing dg, for example, then if you take the derivative of the even elements to even elements, then you just get 1, right? So the top left a corner of this matrix is just a unit matrix. The top right corner is basically this line and its derivative with phi a. So that's complicated. So that part we just leave as it is for now. But importantly, the bottom left element, which is basically this line here, right, of the results, the derivative with respect to phi b, that part is 0, right? So there's no phi b's appearing in the even part of the results. And then this part here, its derivative with phi b is just the exponential there. So the determinant in the determinant, right, we don't need to know this because it cancels with the 0. And so we're left basically with this product of e to the s phi a. So it's a product over half the elements of phi, basically, the even elements of phi. So we can also compute this determinant easily. So that means that we have all the components in order to build up this p tilde, right? To know what that if we have some random variables z that we know how to produce, and then we run this function on the z's to get new functions phi, then we can know what the probability distribution of those phi's are because we have the determinant and because we know how to invert this function. Okay. And also because of the fact that this is just a product here, the determinant, then if we chain many of these together, as is done here, then first of all, the inverse, as you can see, is very easy to compute because it's just chaining the inverses. But also the determinant will just be a product of the determinant. So you will just get more terms here for the other g's that you added. Okay, so to summarize, you have this non-volume preserving flow where you define a function like this to transform your variables. You can chain these in this way. And then since you know you can compute, right? For any given function here, you can compute what p tilde of phi will be. And since there are neural networks involved in this, in these G's, then you can try and find a way in order to tune these neural networks so that this p tilde is close to your desired distribution. Okay, but we're still going to be close to e to the minus s phi over z, right? So then, after you train to get close to this p tilde, you can then treat the chain that you get. So the phi's that come out of this p tilde of phi that you've generated, you can do a metropolis accept reject over those in order to ensure that those phi's do indeed follow the distribution that you want, which is e to the minus s phi. But if you did indeed train appropriately this p tilde to be close to your target distribution, then most of those trials should be accepted, should give you 1. Okay, so how do you do the training? So basically the question is, okay, we said before that you want this p tilde to be close to this e to the minus s phi. But how do you practically do that? So in that case, the loss function, which reflects how close the p tilde is with your desired value is you can define it in this case. So this so-called KR divergence. So, and indeed, what you want is to not compute the logarithm of z. So basically, you need to define log function, loss function, which you don't know how small it can get. Okay. So the minimum of this loss function that you defined here, which is just basically the logarithm of your p tilde, which you can compute, and the action also that you can compute. So this, the minimum you can get of this loss function is minus log z, which in general is not something that you know a priori, right? So one thing is that basically you need to iterate and minimize, and the value of the loss function, other than getting smaller, won't tell you much about how close you are. To check how close you are, you need to do something else, right? Okay, so just one thing that I would like to mention that you can also try if you have any experience in I don't know, running TensorFlow or something, is one, just if you want to check and see if you understand all these concepts. So one trivial exercise that you can do is to try to transform a uniform distribution to a normal distribution. I mean, I know we know how to draw random numbers from a normal distribution. I mean, I just showed you the Box-Miller method, but it is a good thing to try and check and see if you know, if you've understood some of these concepts. So for example, you can define just two affine layers, one that modifies the odd sides and one that modifies the even sides that you can chain. And then in each of these layers, you have two neural networks, S and T, right? And in this case that I'm going to show some examples for you, I just have two hidden layers with 64 nodes each. Okay, so basically that's my phi there. So I'm feeding it in uniform random numbers. And what I want is that these phi's are distributed normally, right? So I define my functions G inverse of 1, G inverse of 2, and this is what it looks like. So U there, which is the vector of uniform random numbers that I've drawn, are split into two, right? So let's say the first half of the random numbers and the second half of the random numbers. And then I have G inverse that is applied to this vector. It gives me another vector. And then I feed that into G2 inverse, right? Which gives me the resulting phi. And okay, one of these G inverse functions leaves the top part unchanged, while the other one leaves the bottom one unchanged. So by the end, I've touched all the elements of the vector. And then this is this affine transformation, which I showed you before. And now S1, T1, and S2 and T2 are neural networks, which means they have a, they have a shape that looks like this. So in this specific case, the input layer, right, is fixed by the number of inputs you have, and the output layer is fixed by the number of outputs you have. But in the intermediate layer is basically the number of nodes is tunable. In this case, I use 64. But that's something that you can, play with. So basically you have 1, 2, 3, 4 neural networks here and their parameters to tune in order to get this p tilde of phi to be as close to your desired distribution, in this case, a normal distribution, to get it as close to that as possible, okay? And and so you can just draw now the curve, which is the normal distribution that you expect. But you can also plot now the distribution of the random phi's that you got. And so after some small number, insufficient number, I would say, of iterations of the training, right? I got a loss function of about 3, and then this, of course, does not look like it's following what you need. But then as you iterate and the loss function becomes smaller, then you indeed get closer and closer to the normal distribution, okay? And in the real application where you want to do this for a lattice gauge theory, as we said, the value of the loss function doesn't tell you much, just the fact that it's going down tells you that you're getting closer, but of course this is bounded from below, from the logarithm of z, which in principle you don't know. For example, this is how, so now I'm showing the training iterations on the x-axis and the value of this log function or loss function on the y-axis. And again, as I said, this is the function that I'm trying to train. You can see that the loss function goes down and stagnates. And in general, in these kind of problems, at least my personal experience is that you should really check your distribution because you won't really know by just looking at this loss function if this is going in the right direction. But in any case, just to see if you want to also check the effect of, for example, why only use 2 affine layers here? Yeah, indeed. So if you use more than 2 layers, then what you get is basically something that might converge to a slightly lower loss function faster. But of course, this has more parameters. These G's, this is a larger chain, so each one of these now has its own S network and T network. So you have more parameters to tune here. So each iteration is more expensive than in the blue case, right? But in terms of iterations, then you get something that approaches faster the minimum. Okay, and so the other thing that I want to talk about then is how this is applied to the phi to the 4 model, right? So this is taken from this paper, which you can also take a look at, but very briefly here, in the 2-dimensional scalar field theory, you have an action that looks like this. So this is a Laplacian term, right? A hopping term. And then you have a squared mass term and then the self-interaction phi to the 4. And then there is a parameter set here that you can define. So basically these E's define this parameter set. So L is the extent of the lattice. It's 2-dimensional, right? So you're increasing the volume here, you're increasing the area of the lattice, you're keeping the bare mass here fixed to -4, and then you're changing this self-interacting term in a way where this this pole mass MP times L, which is a characteristic of the theory, is kept constant, which means that as you increase the area, then in order for this MPL to be kept constant, then that means that you're driving the mass to 0, and that's a critical point. So you have a critical slowing down. You should observe critical slowing down as you move from left to right in the parameters here. And one way to see this is if you plot, and I think I also showed this plot in a previous as a different example, but you compute this so-called 2-point susceptibility of this theory as you're going from the smaller volume here on the top, you're going to the bigger volume to the bottom. So you're approaching criticality as you go from top to bottom. And again, this is the Markov chain here, where I just use Metropolis for this test. So basically I draw each phi from a uniform distribution, and then I do a Metropolis step. And you can see that you get, you see that this 2-point susceptibility changes more frequently at the top rather than this purple here, where you see some sort of freezing. And again, you can compute the autocorrelation length here, which is basically how long do I need to go to see a zero there, defined like this. So that's the autocorrelation time. This is rho of chi-square, and this here is for the small volume, right, which is away from criticality, while the purple is for the bigger volume, which is closer to criticality. And if I compute the integrated autocorrelation time, then you see again that basically the integrated autocorrelation time is exponential with the length parameter here. Okay, and so now so you can do the same thing that I talked to in the trivial example of the uniform distribution. So you can basically train a model in order to have a function that generates these phi's now, and you train it so that the resulting distribution p tilde of phi is as close as possible to e to the minus action. So just I'll flick back now because I want to go to a previous slide. Right, so some technical details. So these phi's now, right, will be functions of whatever the known distribution is that you're feeding into your neural network. So I'll go a bit backwards now. Sorry that I'm doing this. I just want to get to one of the previous equations. Not this one. Right. So yes. So so this S of phi is your action of phi, and p tilde of phi is that process that includes the Jacobian, right? And so what happens in a neural network implementation, if you use some package like the TensorFlow, basically you need to compute the gradients of this loss function with respect to the parameters of the neural network. And just as a technical note, because that might not be obvious, those weights are included in both the action of phi, because phi's are related to the weights of the neural network, but also in p tilde. Okay, so this is not a typical, let's say, machine learning application where you have some known labeled data which you train against, and some and then the model data which you take the derivative over. Another point that one has to make is that there is no so-called input data set in here. So if you're more familiar with other kinds of machine learning applications, so the input in this case is just the original distribution of random variables, which could be uniform or normal, right? And basically that can change with each iteration, or you should change it with each iteration. So there is no fear of overfitting, let's say, because you don't really have any input to overfit on. And so these models are usually called also self-learning, because you don't really need any input to learn on. Okay, so having said that, if you go ahead and try this, then what you will see is something like, right, so something like this is an example of what you get. So these are let's look at the left plot first. So the left plot shows the loss function here as a function of the training iterations. And then with blue, the color coding is with blue is the smallest lattice, which is away from criticality. And then with purple is the biggest lattice, which is close to criticality. And you shouldn't really compare the approach to the minimum here between them, because necessarily these don't use the same number of parameters in the neural networks, right? So the neural networks for the bottom one are more complicated than from the top one. And these jumps here, if you see some jumps, is because this training has been restarted. Okay, so this is not an exhaustive test or an exhaustive analysis. So I should say that this is sort of an incomplete analysis of using these neural networks. But what you see is basically, as I said, the loss function here for the smaller lattice the loss function, as we said, is bounded from below from the logarithm of the partition function. And so you can see that these all approach, a different value, which, as I said, a priori, you don't know it. You don't know what minus log z is. So in order to test how well each network here that you're training is close to the desired distribution, then basically what you need to do, one thing that you could do is to run a metropolis over the generated phi's and see how many of these are accepted and how many of these are rejected, right? And then you can use this acceptance rate as a figure of how well trained is the model, or you can use it as a stopping criterion. So you can say, I will train this until I reach 50% acceptance rate. And so that's actually on the right axis here, not for every iteration, because that would be too expensive, but for every so many iterations, I think in this case, it's every 200 or so iterations, then one generates these fields using the neural network, and then one runs a metropolis over them and then keeps what the acceptance rate is. And so here you can see the acceptance rate for the case of the blue here, how quickly it actually goes up to about 70%. And then the ones that are more difficult to train, that are closer to criticality, actually have a harder time reaching large values of the acceptance rate. So this is basically here the trade-off, right? So the one that's closer to criticality will more likely be more difficult to train, will require more parameters to train, and will require more training iterations to reach a given acceptance rate. So for example, for e to the 5, you see this very slow creep up. And if your target was, 50% acceptance rate, then it might be the case that with this specific choice of the neural network, which means the number of neurons, etc., the number of nodes and the how many layers you put between, you might not be able to reach in a practical amount of time a 50% acceptance rate. In terms of the cost, just to give you an idea, this is not just to give you a ballpark estimate of what all this costs. So this actually was done on Marconi, I see here. Yeah, this was done on Marconi 100, which has these 4 V100 GPUs per node. And if you want to see how many, well, was this running for a day or was it running for weeks? This is the training iteration time in milliseconds, okay? So for the E1 to the E5, you basically have somewhere between 600 to 700 milliseconds. So basically of the order of half a second to 1 second per training iteration. And so you can do the math and see here where it took 100,000 iterations, approximately, how many days that took to reach this point. Okay, and then one can take a slice for a given acceptance rate. So let's say we want to keep the acceptance rate fixed for all of them. It's a bit unfortunate here that this e to the 5 has not reached something reasonable like 50%, but so I think what I did in the next slide is took 50% for these three ones, and then those just took the ones that I had there. So it's not a good comparison if you take them all as a lot, but you can compare the three smaller ones between them, right? Because those have reached 50%. And you look, for example, at the observable. So these are the observable values. So this is just to check that the observables obtained using the neural network to the neural network trained fields, and the observables you get from the metropolis case, just doing the simple metropolis, or the classical case, the non-machine learning case, so that these are consistent, right? So of course this is something that has to happen, otherwise we're getting something wrong. So this is sort of a critical check that indeed observables are the same, whether you generated these fields with machine learning or you generated them with a metropolis. And then probably what you're more interested in is, okay, what is the integrated autocorrelation time comparing these models? So that's it for one variable, for one observable, sorry, tau int of chi-square, and the next one is for the other observable tau int of the energy. And so that's the metropolis case, which increases exponentially. And there it is for, again, for the metropolis case, but now for this other observable, which is the energy, which increases exponentially. And at least for these three, which share the same, as I said, acceptance rate here, you can see that this is more or less flat. And indeed, if you go to the original publication that I have at the beginning of the presentation, so they did it for the full, so they trained all of these to 50%, and they indeed see that this is flat. Again, we're sort of pushing away some of the computational load into the training of the network. But after that has been trained, then the idea is that you can generate these very easily, and you can get as many statistics as you want from the neural network. So, okay, so I guess, so that's actually, I guess we finished a bit earlier than I expected, because this is the what I wanted to talk about today. So do you have any questions?
I do have one on the integrated autocorrelation times, because usually they come, you need to choose a cutoff for the sum. So I don't know, like in the gamma method, there are these windowing procedures, and so I mean, at the end of the day, they come with an error, like a statistical and a systematic one, I guess. So the question that I have is, do you have an estimate for the errors here? Are they just so small that they're not visible, or?
No, I don't have a, I didn't compute the error in this case. But you can see that it's pretty well defined when these go to zero. So so now I'm showing you, right? So now I'm showing you the correlation time as a function of tau, right? And then the integrated autocorrelation time will be basically the sum of these points in principle up to infinity, and you're saying where you stop might make a difference. That's true for, like, if you're doing lattice QCD, where you have a lot of fluctuations here, but because, you know, in this 5 to the 4 model, you can basically beat it out and get a million statistics. I don't think it's I don't think it's really, you know, there's not much error being made in where you stop, right? In this case, as long as you go far enough. You see what I'm saying?
Yeah. So the argument is essentially that the tail is so flat, so like essentially really zero, that The choice of cutoff does not matter as long as you choose it large enough.
Yeah, I mean, this would indeed be a case like in Lattice QCD, where you have like you generate 1,000 or a few thousand configurations. Yeah. Then yes, there you need to take this into account, because there you have meaningful statistical errors. In this case, as I said, I think this is 1 million or something of that order, right? Or a few 100,000 statistics. So the correlation time is really well defined, and where it goes to 0 is also very well defined.
Okay, I see. That makes sense. Thank you.
Okay, if there are no more questions, then maybe I can show you something else if you give me 5 seconds to fix something. So I have a few more slides which were back up, which sort of extend this discussion. So I was expecting to be slower than I was. So if you can bear with me just a second, then I can continue a bit the discussion. Okay. Oops. Okay, so one, sorry. Yes, okay. All right, so this is a bit more involved. Okay, so if nobody has any questions, then maybe I can use the next 20 minutes or so to talk a bit about how one also implements symmetries in these models, which I thought I wouldn't get to because I would be too slow. But, so we just discussed, like before, that you basically have some arbitrary network, and then you just tune it so that p tilde is close to the action, right? And one thing we did not discuss at all is symmetries, and maybe we didn't even need to discuss symmetries, but they do. It seems like they do make some difference. So the symmetries. Notice that the symmetries in this context here, in the context of drawing, variables with some probability, symmetries of the system's action reflect configurations that have equal probability, right? Okay. So if I draw two different phis that have the same action, then they should also have the same probability. So for example, if the action is symmetric under, I don't know, think of this T of F being a translation, for example, then of course P of phi, which is defined like this, should be the same, right? Now, so the problem is that this is not a priori satisfied for the general transformation that we saw in the previous slides, right? So this P tilde of phi won't necessarily be also symmetric under this transformation for a general neural network. So if you just, the way we did it before, where we just used these affine layers here in order to construct our F, then there was nothing enforcing the fact that, for example, if you translate phi by one hop in the X or the Y direction, then S is unchanged. And so P tilde should also be unchanged, right? Right. So if the action is symmetric under one of these transformations of the fields, then if P tilde that we're trying to train on, which involves these functions F, which have the neural networks, is not by construction symmetric, then this symmetry has to be learned within the iterations of the neural network, right? So as you're approaching this p tilde phi being close to e to the minus s, then the symmetry has to be sort of learned, right? So the neural networks, the parameters of the neural network have to converge to a shape of this p tilde, which is equally probable if you shift phi by a translation in the example of the phi to the 4. So that potentially impacts how long it takes to train. So an alternative way is to find a function that can, by construction, be, symmetric under this transformation. So that's what they, there is a letter at the beginning of my slides in the box where I talk about where we're talking about where they define these equivariant flows, which are flows for which these symmetries are satisfied. So by construction, the probability is invariant under the transformation. And there are some conditions which I won't prove, but I will list here for one of these functions being so-called equivariant. So the condition is, one condition is that first of all, the prior distribution, so this R that you put here has to be symmetric, and this is usually trivially satisfied, right? So if this R is a uniform distribution, for example, then of course it doesn't care, then and you're going for translational invariance, and this distribution doesn't care which way the elements of phi, for example, are ordered. And then the other condition is that the transformation should commute through the application of the coupling layer. So basically that if you have a transformation that you want satisfied on phi, then basically you should be able to transform the result of f of phi, and then these should be equal. So if these two conditions are met, then that means that you have an equivariant flow. And again, I repeat, that means that the resulting probability distribution that you're training already has, the shape it needs to have, so that if you give it a transformed phi, it gives the same probability. Okay, and that can reduce training cost. Okay, and then there is a specific case of how you can do this for the case of the U1 pure gauge theory. So I don't need to go through this again, maybe, but in the degrees of freedom in the U1 theory are, e to the I angles, right? Where at each point on the lattice you have you have one of these U's, one pointing in one direction, the other pointing in the other direction. And then the action is written in terms of the plaquette again. So product of the plaquette in this way, and yeah, so basically the plaquette is a product of these U's, and then that means that if you write the plaquette in terms of the angle, it's basically a sum of 4 angles. Okay. And okay, this I already showed. Going down. So what you would need to implement these flows for the U1 is 2 new components, right? So first of all, you have angles that you need to sample. So you need a transformation that maps you from angles to angles. So these neural networks, right? They basically will take as inputs numbers from minus infinity to infinity and give you numbers from minus infinity to infinity. So you want to be able to map the angles that you input to angles of output. And so you use some sort of mapping like this one here, where if z is an angle from 0 to 2 pi, then this x of z maps you from minus infinity to infinity. And then this also has an inverse. And so you can chain it at the beginning and at the end of these affine layers in order to in order to do this mapping, and it's also differentiable, etc. Okay, and then you also need a transformation that preserves, in this case, gauge symmetry, right? So basically, if gauge symmetry means that if I transform a link variable by a local gauge transformation like this one, so basically a U1 variable at each site, right? So that's a local gauge transformation. So if I transform my fields with an arbitrary of these omegas gauge transformations, then the action is unchanged because the action only depends on the plaquette. And so it's desirable to have one of these p tildes, to have one of these transformations that has already built in this transformation, so that the p tilde that you get out is actually invariant under a gauge transformation. And so, okay, so now this is getting a bit technical, but the way to do this is to, as we did in the phi to the 4 model, where we just had half of the variables being transformed here and the other half down there. You do it in the same way, but now you have half of the links being unchanged, where the other half of the links are modified according to this staple argument here, okay? So probably it's not useful to do this now step by step, but you can see that this definition here will actually, is actually one of these definitions where the gauge transformation commutes with the application of the affine layer. Okay, so yeah, it's basically, so you can show, if you follow this through, that basically if you transform the links inside this transformation H, then the omegas that will appear here, the gauge transformations, will actually, you can write them, you can follow through and see that these can be written outside, so that the gauge transformation commutes with the application of the phi to the 4 field. Okay, and then it's just a matter of defining this H, which is basically, again, looks something like this. So H is again a transformation that leaves some of these untouched, while touches the remaining of them. And then it's basically another translation and shift, as in this case. But of course, this is not applied to the angles, but applied, as I said in the previous slides, to a mapping of the angles to -infinity to infinity. Okay. So that's my backup slides exhausted. Does anybody have any questions?
Yeah, maybe I have a naive one. Since I never worked basically on this neural network implementation, can you maybe spend some few more words on how to, or even to hint on how to basically implement this, what you call T1 and S1 in such a way, with these node structures, in such a way that you will approach these the function you desire, basically?
Well, it doesn't, yeah, so the thing is, it doesn't really matter what those S and T's are, right? So the fact that they're neural networks is just because that's a convenient tool. So maybe I can go back to this picture that I had, the purple boxes, pink box.
Yeah, exactly.
Okay. So you can, a neural network is nothing too complicated, right? So basically you have floating point numbers on the nodes, right? And the lines just mean that there is some operation being done on this second layer of nodes here. Some linear combination of these are taken to determine the value of each of these nodes, okay? So there are some so-called weights. So there's some parameters on each of this node. We determine what linear combination of these 4 I will take to determine the value of this guy. Then there's some different weights on the second one here. Can I zoom in? No. Oh, destroyed it. Sorry. Try to zoom in and I close the presentation. So there are some weights defined here, okay? Some parameters, which basically all they do is they determine what linear combination of these 4 will be taken in order to fill in the value here. And some different weights for determining the value here, some different weights here, etc., up to the last one. And then in the second layer, this is repeated. So now you have some different number of weights there that determine what linear combination of all of these now will be taken to determine the value of that point. Then there's some different weights here that do the same. They determine what linear combination, again, of all of the 64 that I have here in this case to determine that value. And so on until you reach the end and then you have some output. And I'm oversimplifying things here because you can also do different things like put a cutoff to the value that you want to output. Some of these, this does not have to always be fully connected. In this case, everything is connected with everything, but that's not necessarily true. You can have, for example, convolutional layers which only take a window of the input. I am oversimplifying it with the way that I described it here. But that's the main concept, right? So it doesn't really matter what T1 is and what S1 is. What matters is that you have some parameters that you can always differentiate over, right? Because they're just linear combinations. So you can take the derivatives. And so that means you can always find a gradient towards, you can always find a gradient of the loss function with respect to these parameters. And there are sophisticated software that, you know, provide you a very high level interface to all this stuff. So you don't really need to think too much about how all this is implemented. But the gist of it is that, that's basically you have some parameters here that you can take derivatives over, and they're just generalized functions. You can think of them as a function that is very general. It has an arbitrary number of parameters. And so you can train it to give you an output that you want.
So in this example, for example, these 2 hidden layers are basically this central line here, yeah, of the picture, and each of them has 64 nodes that are just a linear combination of the starting 4, basically.
Exactly. So okay. Yes, so each one of them is some linear combination of it. If it's fully connected, which in this case it was, then it's a linear combination of the starting 4, and then each one of the next 64 is a linear combination of the previous 64.
Goes into the second hidden layer. Okay, yes. Now I got it. Thank you.
Yeah. Any other questions? No?
Maybe one, not sure it makes sense. I was thinking when you talked about gauge invariance that has to be implemented, this is all done in 100% gauge invariance setting, right? There's no gauge fixing in any of these ideas, or?
Yeah, I think yes. I think one way to do it would be to fix the gauge. I think there is some work on using this machine learning to generate gauge fixed configurations, and there, because the gauge is fixed, you don't need to worry too much. I don't know the details, but I have seen a paper where they did this with gauge fixed configurations. That was your question.
Yes. I mean, I don't understand much of this either, so I was just thinking whether gauge fixing has a role in these studies. Thank you.
Well, yeah, but what I think the idea is there is that you train a neural network in order to generate fields at a fixed gauge, and then it doesn't have to, this expressive function that you've defined doesn't necessarily have to be equivariant under gauge transformation anymore. So that sort of restricts your function in a different way. That's how I understand it, but again, I don't know the details of that.
One would have to take into account this gauge fixing at the later stage somehow, some other term, or right?
Yeah. So then when you do, when you run measurements over the generated configurations, you need to, yes, take that into account somehow.
Thank you.
So this is not really HPC, but it is computing aspects of lattice gauge. So one thing that one has to keep in mind is that so far these have all been shown for small systems, relatively small systems, which can fit on a single node or in a single GPU, right? And if you think about like configurations that we're using in Lattice QCD these days, at the moment it's not obvious how one would even do this for those kinds of sizes, where basically on this side here, in the input layer, you have millions of inputs. So just want to, raise a flag here and say that this is all very early. This is early stuff. They're moving. This field is moving fast, but still, it's not quite clear how one scales this, if this is even scalable to contemporary state-of-the-art lattices.